All right. So we were here at example 2, and we talked about this trunk of a tree that had a height of about 18 meters and a base diameter of about 0.5 meters. Can you guys remind me what we did for part A yesterday? We said the wood has a density of 550 kilograms per what? I'm sorry, 550 kilograms per cubic meter. It says find the mass of the trunk to the nearest kilogram. So I think yesterday we started out by saying, well, we need to remember that the density is equal to a mass divided by a volume. Was that right?
Yeah.
And up top, I think I said, assume that this tree trunk was what shape particularly?
Cylinder.
Okay, so we said assume that this is a cylinder. Okay. So here we go. We knew the density was how much here, kids, yesterday?
550.
550 kilograms. Okay. And that was going to equal my mass, which is what we're trying to find. We were trying to find the mass right here of the tree trunk, which was cylindrical. And that cylinder had a height of how many meters, kids? 18 meters, and was how much of a radius or diameter? I'm sorry. Okay. So the mass is what we were trying to find. What formula did we use yesterday for this volume? You guys remember?
Pi r squared.
Times what?
The height.
Pi r squared times the height. That's the volume formula for a cylinder. So I believe yesterday we put pi. What did we put in for the radius yesterday, kids?
0.25.
Oops. So pi times radius squared, and then what was the height again here, kids?
18.
Okay. So what we did, I think we set a proportion up, and we did all those numbers. We crunched all those numbers. What did we end up with for mass yesterday?
1,943.8.
Okay. 1,900, did you say 43?
Yeah.
Point.
86.
Okay. This was a mass that we were looking for, so what type of unit should you attach to that?
Kilograms.
You bet. Okay. All right, so again, everything kind of feeds off this idea that density is equal to mass divided by volume, and we just have to put in the information that we know to help us solve for what we don't, really. Okay. So let's take a look at what's happening here in part B. We're talking about this same tree, and over time, these trees do what?
Got bigger.
They get bigger. Okay. So it says the trunk puts on a growth ring of about half a centimeter this year, and its height will increase by about a quarter of a meter. How many cubic meters of wood will the tree gain after 1 year? You guys all know about tree rings, don't you?
Each year gets one.
Yeah, so if you cut into it and you see all the rings, you can say, well, this tree's been around for that many years. Okay. So the tree ring is growing at about half a centimeter each year. So each ring, if this is my center and there was a ring right here, the next ring would be how much further out? Half centimeter, right? So how much does the radius change each year then? Half centimeter. So what would your new radius be then? If the old radius was 0.25 meters, what's the new radius going to be? Anybody have a guess? Okay, this is kind of tricky. Remember what we said about units yesterday?
Don't they have to be the same?
They all have to be the same. And how is everything measured up here, kids, in terms of length for your radius and your height?
Kilograms. Wait.
What's it say at the very top of your page in terms of the radius and the height for your tree? How are they measured?
Kilograms.
Well, the mass is in kilograms, but how about the lineal units?
Meters.
Meters. Everything's measured in meters. All of a sudden, they come in here and say, hey, by the way, this is growing at half a what?
Centimeter.
Does that unit match exactly what you started with? So probably a pretty good idea to turn centimeters into what here, kids?
Meters.
Meters. How many centimeters are there in a meter?
100.
100, yeah, 100. Okay. So it would probably be wise of us to take this 0.5 and divide it by what value, kids? Okay, so here, this 0.5 centimeters is going to be the same as 0.5 divided by 100 because there's 100 centimeters in every meter. This is actually going to be equal to 0.005 meters right here, all right? So my radius is adding 0.005 meters each year. Okay. How about the height? How did the height change in that year? What did that increase by? Quarter of a meter. Is that unit, is that going to work for us? Is that something we like right now, the way this is set up? Absolutely. So this is going to grow at half a meter, okay? So height adds quarter of a meter each year. Okay, so it says at this point right here, after this quarter meter right here, it says how many cubic meters of wood will the tree gain after that 1 year? Okay, so let's find its new mass. All right, let's find its new mass. Okay, to begin with, what was the mass up here? What was our original mass, kids? What was our original mass?
1,943.86 kilograms.
Okay, so we're going to go through and do the same thing. We're going to find the mass now after this has changed a little bit, after it's grown for a year. Okay, we're going to follow the same process. So here we go. The density is still going to be what, kids? It's the same tree, so the density is still going to be what? Yeah, it's still going to be 550 kilograms per cubic meter. We're looking for how much mass we have now. But now we have some new units in terms of radius and height. Okay? The radius originally was 0.25 meters, wasn't it? But how much am I adding now to it? So what's 0.25 plus the 0.005 meters of growth in the radius? Anybody? Should be easy.
0.255.
Yep, 0.255. Radius squared. What's my new height now, kids? What was the original height? 18. How much did it grow this year?
2.5.
Okay, so the new height now this year is 18.25. Okay. You guys take a minute and see what you come up with for a value there. I'll do the same as well. Okay. See what our new mass is. Obviously, if the tree grows, what should happen to the amount of mass in it, kids? It should go up. So my answer is going to be more than 1,943 or less. Better be more. Okay. So I'm going to do this as well. Times.
Got 3.7.
Okay, let's do this. What do you get for a total mass first? I've got something a little different. Is 3.7 going to be more or less than this right here?
Way less.
We want our total mass in the end to be more than this right here, right? What are you guys getting for a value?
I got 3.5.
Okay, something's not quite right there. I think, did you divide by 550 or multiply by 550?
Oh, I didn't do that yet. was just finding the bottom.
Oh, the bottom?
Yeah.
Okay. I want to solve the whole thing for mass. And maybe it would help you if I put this over 1. So really it's a proportion. Take 550 times this whole mess down here and then divide by 1. That'll get you a new mass, won't it?
1,170.85.
Okay. I've got 2050.4812. Anybody else with 2050 when they did that? Run it one more time. I want to make sure everybody gets the same one. I'm going to go ahead and call this 2050. .48 kilograms. Does it make sense it would be more than what we had up here? Does it make sense that 2050 would be more than the 1,943? Why? Tree grew. It's going to gain mass, all right? Okay, now the next part of this, did you guys all get 2050? Okay, is there anybody that's not getting that? Okay, now the next part on this says, hey, if that tree continues to grow at the same rate for the next 5 years, will it gain the same amount of wood each year? And explain. Okay, well, could I figure out how much mass it changed from here to here? Could I figure that out? Okay, let's see if it's changing at the exact same rate. Okay, let's see if we're adding the same amount each year. How many think it's going to add the exact amount, the same exact amount each year? How many think maybe it won't? Okay, think of a really little tree. I mean, over years, you got to remember it grows this way, and what other way? Up. Okay, so let's check and see what happens here. We'll figure out the difference. Somebody do this for me real quickly. Figure out the difference between this and this. How many kilograms did we gain from the very first year to where we're at now, 2050? Take the difference there, okay? I'm going to write this off to the side of the board. 106.62 kilograms is what we've gained, right? Okay, so let's do this, kids. Let's add another year here. You don't need to write this next one down necessarily, but follow along with me. How much of a meter am I going to add for another year to its radius? This would be tenths, hundredths, thousands. So I'm going to add 5 thousandths of a meter, aren't we? Okay, and then how much of a meter am I going to add to the height? Okay, so this 0.255 is going to turn into, if I add 0.005 to this, what's this going to turn into for a new radius? 0.26. What's this going to turn into for a new height the next year? 18.5. So let's run those numbers and see what happens here. And we'll see if we gain another 106 kilograms. So you don't need to write this part down, but my density is going to equal the mass over the volume. We want to find the mass again for the second year. What was the density going to stay at constantly again, kids? How many kilograms per cubic meter? 550. And now we're going to look at this. We're going to say, well, the mass is now going to equal pi times, what'd you guys say the new radius will be in that second year? Was it 0.26? Is that what I remember hearing? 0.26 squared times the height, which is going to be 18.5. Okay, I'm going to set this up as a proportion. So I want to take 550 times this big mess down here below m and divide by 1. So let me pull a calculator here and we'll check this out. No, you don't need to write this down. I'm going to go 550 times what first, kids? Times, oh, I hope this doesn't screw up. I screwed that up, didn't I? No, I didn't. No, I didn't. I've got that right. Times 18 point. What do I end up with here, kids?
2,160.
2,160 here, okay? So I'm going to write this down again, and we'll see where we're at. $2,160. What did we have in the previous year?
2,050.48.
Okay, so if I do a second year here, we end up with, and I'm just going to write this kind of over here, jot this down, make some room here quickly. Okay. So that second year, or that first year of growth, we got 2050, and now I put down here that we had a second year where we put some numbers in here. What did we get for a value? 2160 point. 88, okay. .2160 kilograms for that second year. Okay. Guys, what's the difference between 2160 and 2050? What would 2160 minus 2050 get you? 110, right? Okay. So it'll be a change of 110 kilograms. I have a question right up here. Are these two values exactly the same? No, they're a little different. Okay. And the reason being is, guys, when trees get bigger and bigger and bigger, they've got to account for more. What happens to the amount of wood going around? Each ring, if you could cut each ring out, what's going to happen to the size of that ring each time? The ring is growing this way, and it's also growing what other way? If you start from the very bottom and watch that tree grow, if you cut that whole trunk right there, guys, it's growing both left and right, front and back. You know, it's going horizontally in all directions for a radius, but the height is also doing one as well. Changing. So each ring is getting bigger and bigger and bigger. And if I have bigger rings in terms of height, what's going to be true about the amount of mass that you add each year? Is it going to stay the same, or is there going to be a little bit more each year? It's going to be a little bit more each year. Okay, so the answer to that question is, will it gain the same amount of wood each year? The answer is no, because it continues to grows out, but it also grows what other direction, kids? Up. Okay. So you're changing two dimensions at the same time. If you were changing just one dimension, the same constant rate all the time, things would work. But we're changing more than one dimension. Okay? Whew, this is tough stuff. Whole idea, remember what? To start these types of problems, kids.
The same like thing.
Want to make sure we're working with same units, and then what formula are we really concerning ourselves with every single time with these problems? Absolutely. Think density. Think like units, think density, okay? All right, this is another tough problem. One more example, and then I'm going to let you get working on a few things here. Let's talk. Using a volume formula. What type of shape are we working with here, kids? Cone-shaped pile of road salt has a diameter of 24 feet and a slant height of 14 feet. After more road salt is delivered, the linear dimensions of the pile are 3 times the original dimensions. Okay? It says, how does this affect the volume of the pile? Okay? I kind of gave you the answer here already. All right? What are we doing to all of the dimensions here, kids? Multiplying by 3. So I want to kind of show you what's going on here. I kind of gave you the answer, and maybe you want to underline that this is the answer right here. If I change all of the dimensions by 3, if you change every single dimension by 3, multiply it by 3, what do I put in red right there? What am I telling you? Somebody read that last sentence to part A for me.
The volume of the pile after more road salt is delivered is about 27 times the original volume.
Okay, without even doing any work, anybody know how they came up with that? They started with a cone that looked kind of like this, all right? You guys all know what a cone looks, okay? And what they did is they changed the height by 3 times. That height went up 3 times higher. It went horizontally, left and right maybe for you, 3 times wider, and then front to back 3 times deeper. Okay? So I multiplied the height by what value? 3. I really kind of multiplied the length by 3, how far left to right it is, and then the pile forward to backward multiplied by 3. Anybody have an idea how we came up with that 27 up there that's already in there as an answer? 3 times 3 times 3. How many dimensions did we really change? Yeah, well, 3 times 3 times 3 is 27. When you change all 3 dimensions by a factor of 3, that has the same effect as taking it times 3 different times. It's basically like 3 to what power, kids? 3 to the third. I just want to show you real quickly the following. Get this down and make sense of this. If I change the dimensions by the same scale factor all the time, in other words, triple every dimension, that's the same effect as cubing that for its volume change. So in other words, if I say height's 3 times higher, the length is 3 times wider, and the width is 3 times deeper, then it's like taking the original value and multiplying it by 3 how many different times? 3 times, and that 3 times 3 times 3 is 27. So quickly, kids, I'm just going to tell you this right here. Volume formula of a cone. Well, you know what? I think we're okay with this. Are you guys okay with this right here? You understand why it's 27 times bigger? What if I would have done this? If I would have said, here's this salt pile. It's kind of a cone shape. Here's that salt pile. It's kind of a cone shape. What if I tell you I double the height and I double the, what if I double all the dimensions to this? How many times bigger is the new pile than the original pile?
4.
I heard 4 and I heard 8.
8.
Okay, we're talking about volume now, right? What kind of unit? It's a cubic unit. And 2 to the third power. 2 times 2 times 2 would be, make sense?
Wait, so it's, say the question again?
All right, so if I doubled all the dimensions on that, so if I made that 2 times higher, 2 times wider, and 2 times deeper.
Okay, so it's always to the third power.
If we're dealing with volume, exactly.
Okay.
You okay with that?
Yeah, that makes
Okay.
sense now.
All right, what if I went 4 times on all dimensions, kids? 4 times 4 would be, times the third 4 would be 64 times the amount, okay? All right. Okay, so let's see what's going on here on this last page here. It says a lane mile in an area of pavement that is 1 mile long and one lane wide during a storm. It takes about 250 pounds of road salt applied for every lane mile. So here's the deal. If this is a lane on a highway right here, if this is 1 lane, by 1 mile, how many pounds of salt does it take to treat that road during a winter storm? How many pounds of salt does it take to treat 1 mile of 1 lane? 250 pounds, okay? Okay, so right here it says estimate the number of lane miles that were covered with the road salt during the storm. A cubic foot of road salt weighs about what? 80 pounds. So I'm going to back up and take a look here at what we had on the previous page here. Okay. So it says a cone shape, blah, blah, blah. I think I forgot to type something in there. Let me check here quickly. So we're going to put a little bit more information with this up here. And figure this out here. Okay, so here we go. Okay. Perfect. I think we've got it all. Are you ready for this one? It's going to be a toughie. So right here, a lane mile again. How many pounds are here? Okay, it says a cubic foot of road salt weighs about what? We've got to figure out the number of miles that were covered with the road salt during the storm, okay? When we took all this salt right here, we added a bunch of salt to a pile, right? Okay, what shape was that pile of salt? Cone. So let's draw our cone of salt here, all right? So just make a sketch kind of like this. I like to draw an oval, kind of like this. And I'll make this kind of hollowed out here. Actually, I'll shade that real light. I don't know, that'll work. That's a little darker. That's a little better. Okay, you guys should make an oval and then just kind of make, if you can, kind of a, it's the best I can do for a cone. Is that okay for you guys? Okay, looks like a cap I used to wear a lot when I was in elementary school in the corner. And it wasn't a happy birthday party cap either. Anybody know what cap it was? Anybody heard the dunce cap before? Probably a little ahead of your time. Okay, I'm going to jump back and forth here a little bit. You guys need to help me out here. Okay, so here's the deal. It says the original pile, a cone-shaped pile of salt, has a diameter of what? 24 feet and a slant height of what? 14 feet. So I'm going to go ahead. It says, we'll put these in here. That'll work for us, okay? So let's do this. What's the diameter again, kids?
24.
24 feet. Oops. So the diameter all the way across this is 24 feet. They gave you a slant height here, kids. What's the slant height? 14 feet, okay. Okay, so we need to first of all do the following. Salt here has a certain volume. Take a look at your last page. What's the volume formula for a cone? I think we wrote down there, did we write down pi r squared times height divided by 3 for that yesterday?
No, we didn't.
Okay, so let's do that right now. Okay, I like this formula for cone better. So on this cone right here, you might want to write down that the volume formula for this is pi r squared times height divided by 3. Okay, so let's find the volume of this right now. Okay, let's find the volume of the salt pile we have. Using that formula. Okay, so we're going to go pi times, let's see, if the diameter of that pile is 24 feet, kids, what's the radius? The diameter is 24, what's the radius I would plug into the formula? Be 12, wouldn't it? Half of 24 would be 12, wouldn't it? Okay, now we have to be very careful on this. The height that we're talking about for a cone right here is on the inside part here. It's not this slant height that they give you of 14 feet. So kids, what we know right here is the radius is 12. This is assumed is a right angle. How are you going to find this height right here, kids? How would you find the height of this cone first? Yep, so I'm just going to do some quick things over here. My height, h. My height, I'll go h squared plus 12 squared would have to equal, which is 14, right? Okay, so I'll crunch some numbers for you real quickly, save a little time. H squared plus 12 squared. Anybody know 12 squared?
124.
Anybody know 14 squared? Very good, 196. Good job.
Thanks.
Help me subtract on 44 now, guys.
52.
Very good. All right, let's go 2 places on the height then. So take the square root of 52 for me. Got to be close to about 7.2, isn't it?
Yeah.
7.21, we'll call it, maybe for a height. Now, since it's a cone, by formula, what do I have to divide by now here? What do I have to divide by?
3.
Yep, divide by 3. Okay, so do this for me first. Okay? See what that value crunches out to be. You go pi times 12 squared times 7.21 divided by 3. What do you guys do? Don't be shy. Yell it out at me.
Hold on a minute.
That's all right.
$1,087.24.
1,087.24. And this was all measured in what unit, kids?
Feet.
Okay, so this is 1,087.24. Everybody agree 1,087? Okay, just want to make sure we've got some agreements on this. Now, guys, those dimensions were for the pile before the storm because we knew the storm was coming. And typically, if people know storms are coming, what do they do to their salt pile? Well, they lay it out, but before the storm hits, they might want to add to that salt pile, right? Okay. I'm going to write down that this is the volume of the original pile. The original pile is 1,087.24. What kind of unit should this be? It's volume, right? So it should be cubic feet, right? In part A, what did we do to that pile? If I look back here in part A, what did we do to that pile? What did we do to all the dimensions?
We cubed it.
We tripled them, right?
Yeah.
Okay, and we said tripling all dimensions means we have how much more or how many times more salt? What did it say here?
27.
So we have 27 times the amount now from what we originally had. Would you agree with that? Because we tripled all dimensions. So I'm going to go back to this right here and say, okay, this is what the small pile was. It was 1,087.24 cubic feet. But we tripled all the dimensions. So tripling all dimensions really had the same effect as taking that volume and multiplying it by what number? If we went and tripled the height, the length, and the width. It was like taking that value times 3 how many times? Yeah, 3 times 3 times 3 times 27, but we tripled all the dimensions. So the big pile, so I should write this. So the volume of the big pile is 1,087.24 cubic feet, and it's 27 times bigger now. Okay? Somebody calculate that for me. 1,087 times
2,930. Oh wait, 29,355.
29,000 Say that one more time for me, Jaden. 29,000.
355.
355.54.
0.48. It's because I used all the decimals. She's talking about the decimals. I didn't use 1087.24. I did the rest of the decimals.
Oh, okay. You know, how about we just call it 0.5? Can we all be happy with that?
Yeah.
Okay. So 29,355.5 cubic feet. This is important. Okay. In terms of volume, how much salt do you have right now? Okay, this is the amount of salt we have right now. Now, I've lost sight of what the heck the question's even asking. So take a second and go back and read that. What the heck is your question even asking you right now?
Estimate the number of lane miles that were covered with the road salt during the storm.
Okay, 1 mile of one lane. 1 mile of one lane. How many pounds of salt does it take? How many pounds of salt does it take? 250, okay? It also says right here, they give us a little conversion factor. They say, oh, by the way, this big pile of salt that you have says 1 cubic foot weighs how much? So the density of the salt would be like 80 pounds per what? Not quite. Listen to what I said. The density of my salt is 80 pounds per, this is an important statement right here. The density of my salt is 80 pounds per what? Read the sentence.
Cubic foot.
Per cubic foot, okay? Everything ties back into density. So this is where things get pretty important. We know that it takes 250 pounds to cover 1 mile of one lane of highway to make that safe. However, we have this big pile, and this big pile down here, how many cubic feet do we have in our big pile now, kids? Okay, we got to figure out how many pounds of salt we have right now, don't we? We have to figure out how many pounds of salt. We got to find the mass, all right? So here's the deal. If the density of the salt is 80 pounds per cubic feet, or per cubic foot, if you will, we've got to figure out how many pounds we have. Well, guys, if 1 cubic foot is 80 pounds, how many cubic feet do we know we have? Okay, so let's solve the number of pounds. We're going to have 29,355.5 cubic feet here. Somebody solve that proportion for me. Whew. Algebra math. Going to Harvard.
Imagine Gassman trying to teach this to us. Is this going to be a really big number?
It's going to be a big number, kid. It's going to be in the hundreds of thousands, I imagine. Maybe close to even a million.
2,000,000.
Okay, I like it.
348,440.
So my salt right here, kids. Try and squeeze this. How much salt do we have? Say that again.
2,348,440. Just.
I missed. I totally am. 2 million. I caught that part.
2,348,440.
440 pounds. Okay, we have 2,348,440 pounds of salt. Okay? Are you there with me right now? Okay, so that's good to know. I have a question. What's the problem asking us to do?
How many lane miles?
Find the number of lane miles that that pile of salt could
Cover.
safely cover. Whew, we're getting close, right? How many pounds to cover 1 mile of one lane, kids? How much? 250. So if I know that, kids, we are so close on this. This is cool. I'm almost out of paper. We might as well just stop, right? Nah, no. Wrong answer. All right, sorry, that was a little crazy, but that's okay. Okay, so 250 pounds of salt now covers 1 mile. Kids, how many pounds do you have? How many pounds of salt do we have?
2,840.
Okay, so if it takes 250 pounds of salt for 1 mile, wouldn't that be the equivalent of 250 pounds is to 1 mile as 2,348,440 is to X miles? Would you agree with that? Okay, so I'm going to write this 2,348,000. I'm going to try and squeeze it in there over X miles. You guys solve that for me, okay? Holy cow. I'll do it. I'm going to take 1 times 2 million.
Wait, no, I got it.
Okay, hang on a second. I want to do it too. I don't want to miss out on the fun. What'd you get for an answer?
Hold on. Okay, is it 9393.7?
9,393 miles. Holy cow. $9,393 miles. That is a tough problem. Okay. First thing we had to do was understand how to find the volume of the initial pile. And then we knew a storm was coming, so what did we do to the salt pile even before we went out? Tripled every dimension, which meant we had 27 times the amount of salt. Then we had to take this idea that the salt's density was 80 pounds per cubic foot to figure out how many pounds of salt we had. And then we had to use the idea that it took 250 pounds of salt to cover 1 mile, and use that idea to figure out how far we could safely salt. 9,393 miles. How far is it across the United States? About 3,000 miles? That's a lot of salt. Okay,
Is that going to be a question I got on the quiz?
maybe. But you have stuff in front of you, right?
Yep.
Okay, that's a tough question, all right? I'm going to go ahead and stop there.